Hello everyone, this is part 3 video on heat pump experiment. We are looking into the calculation of COP for the heat pump. It is given by the ratio desired output over required input. The output here with the heat pump is the amount of heating taking place in the condenser region, how much of heat is gained by the water or how much the water is heated to. So it is Q in the red bucket given to the water, and to achieve that heating there is some input required, which is the electrical energy given to the compressor. So it is either the compressor work or compressor power. I have written W work here so that it is in the unit of joule, and Q is also in the unit of joule. They cancel out and at the end you get a number. It is a dimensionless number. Usually the COP is greater than 1. Higher the number, the better is the performance. So the normal numbers are like 2.5, 3, 3.5. It could be any number in that range. And like I said, the higher the number, the better is the performance of the device. So now we want to find out Q and W from the data that we have collected, and let's go here and see how we compute Q. Heat gained by water in the red bucket, the very famous equation mCp delta T. So m is the mass of water in the red bucket. It is a 5-liter bucket, so it's almost same conversion. 5 liter approximately you can take as 5 kilogram. Cp of water 4180 and delta T of water in the red bucket. Now we are not focusing on the green bucket, so you all also have those temperatures with you, but for this particular exercise we are not going to use the numbers or the temperature values from the green bucket. So delta T is the change in temperature of water in the red bucket, T final minus T initial. So I have another equation here trying to illustrate the same idea. Final, if we choose as 15 minutes run time, the final temperature of water in red bucket will be at after 15 minutes, and the initial temperature at time 0 when we start. So basically it will be room temperature. Time 0 temperature will be the room temperature when you start the experiment, and then assuming we run it for 15 minutes, so the final temperature will be the temperature at 15 minutes. So this delta T, both of them measured in the red bucket, will be plugged in here, and when you multiply all of that, you will get the heat gained by water in the red bucket with the unit joule. So that completes our numerator part. Now we are trying to find out the compressor work. Again, here as an example I have put 150 watt. There is a joule and watt meter which gives you the compressor power consumed, direct reading with the help of the device there. So let's say I measured and I found it to be 150 watts. After 15 minutes you will write down this reading. So it keeps fluctuating from time 0 until time 15, but let's pick the number that we observe at the end of the experiment. So this is as an example 150 watts I have chosen here. So I want to compute the work. It is power multiplied by time, and then 150 watts as an example, and time we have chosen 15 minutes, so multiply by 60 seconds. So then you have the second cancelling out there, and you'll get the unit of work as joule here. So like I said, if you get 125 watt, you'll put 125, and time duration selected 15 minutes, you'll get the work here. So that work again you will bring in this main equation for COP, and after which you will get the final result of the COP. So again, this is how you calculate the heat gain by water in the red bucket, and this is how you calculate the compressor work with power measured directly from the joule and watt meter. Okay, so there is a graph which I have already explained to you in part 2, where you do data collection. The manual also gives you the sample graph. time on x-axis and temperature on y-axis. So you will put both the temperatures, temperature of water in blue bucket and temperature of water in the red bucket. Blue means it is here a green bucket. Okay, so both the bucket temperature of waters you are going to plot it in a graph, and then you can differentiate that on one side you have the temperature increasing, another side you have temperature decreasing, which means heating effect and cooling effect you observe on the same setup, and then you realize that the same setup can be used for either of these applications. Okay, that is all about this experiment. See you in another video. Okay, bye.